This is a presentation of our paper, PHYjacking, Physical Input Hijacking for Zero Permission Authorization Attacks on Android. We are a group of researchers from the Chinese University of Hong Kong. Clickjacking was once very popular in browsers. Attacker tricks users into clicking on some overlay button. When the victim thinks he's interacting with a game, he's actually clicking on the payment confirmation button in the background. On mobile platforms, this kind of authorization, people sometimes call it tap-jacking or touch-jacking. If we view screen tap as just one of many physical inputs on mobile, it's natural to think about generalization of this kind of authorization hijacking attacks to other inputs, like fingerprint and camera. Nowadays, people use fingerprint scanning or face recognition in authorization scenarios to perform sensitive actions like payment. Are modern mobile platforms like Android secure enough to block this type of attacks? How difficult is it for attackers to launch this type of attacks? This shows what we achieved in the end. These are screenshots of the authorization hijacking in some real apps with different physical inputs. Some are for payment and some are for permission granting. So how did we do that? In general, we assume that there's a malicious app running on the victim's Android phone. Then the malicious app can somehow set up a confusion scenario where the target app is waiting for physical inputs for authorization, but the victim cannot see or understand what is going on and is tricked into feeding the physical inputs. In practice, the malicious app can put the target authorization window underneath a malicious covering window. This is possible because Android allows windows or activities from different apps to be stacked together. So we need to propose confusion setup techniques to create such layout while not blocking the background input listeners. We abstract out the workflow and call the framework PHYjacking, which stands for Physical Input Hijacking. To make it work and make it practical, there are two major challenges. First is that we need confusion setup techniques that require no special permission. Second is that we need to bypass any OS level or app level mitigations, which detect and interrupt background physical inputs. We cannot just reuse existing techniques to solve those two challenges. For example, Android floating window with the draw over other apps permission are widely used for UI redressing attacks, but it requires a special permission that has raised much attention. We want our malicious apps to be zero permission. This is an overview of our new techniques. Attacks in red boxes are on the right part are our new attacks. Comparing to existing attacks which rely on some unusual permissions, our attacks exploit both apps flaws and system bugs to achieve hijacking for a wider range of physical inputs. Simplified Android activity lifecycle model, which is a state machine for Android activities or Windows. In a typical authorization scenario, the authorization is started after the corresponding activity is launched. The activity stays in the foreground with the resume state. If later another activity jumps to the front, the authorization activity goes into the pause state and then stop state. Meanwhile, the authorization process should be blocked. For example, it should stop listening to the fingerprint scanner. In the attack setup, the malicious app can invoke the authorization process by launching the target activity. This is possible because some apps tend to support invocation from other apps to provide functions like third-party payment. Right after that, the malicious app can bring a prepared activity of its own to cover the authorization activity. And optionally, it can also display something to trick the user into feeding the required input. Note that on Android, Those two activities can even be launched at once. Simple confusion setup like this works in some cases, like tap-jacking in some apps. But for apps with protection mechanism or for other physical inputs like fingerprint scanning where system-level mitigations exist, it won't work. Let's first take a look at what can apps do to protect themselves. They can stop listening to physical inputs in the unpaused event, because it is always the first event when an activity goes into the background. So apps can use it to detect when it's switched to the background. But many apps do this incorrectly. They either do not have this protection at all, or they only cancel the listener in the unstopped event. Well, so why do we say that cancellation in unstopped instead of unpause can cause problems? That's because an activity can also stay in the pause state and not fall into the stop state if it is considered visible in the background, which many developers may not know. This can happen when the covering is a translucent activity. What's even worse is that the system do not care if the translucent covering is truly visually translucent. So the attacker can simply launch a malicious covering with the translucent property while setting it to fully cover the victim activity underneath. If the target app only implements the input cancel logic in the unstop event, it will continue to accept physical input in the background, giving no context to the user. We call this type of attack method translucent attack. So this is about exploiting apps' improper implementation. What about Android OS? Are there any system-level mitigations against such attacks? First, for camera and microphone on Android, background access are banned starting from Android 9 according to the documentation. However, the definition of background here might not be what's in your mind. It only means background service, but not normal activity that is being covered. So apps still need to rely on correct implementation to prevent camera or microphone hijacking attacks. For Fingerprint, the story is more complicated. Android starts to provide Fingerprint API since Android 6, and only add background access check starting from Android 9. That means Android 9 is to check whether the fingerprint listening activity is in the topmost foreground. This check is performed whenever the activity stack changes. If the check fails, the fingerprint listener will be interrupted by the system. However, this checking scheme misses some corner cases, based on which we propose some bypasses. One example of the bypass is called Wake Up Bypass. We first launch the covering as usual, then the background fingerprint listener will be killed because the checking is triggered during stack change. Then we wait till the device sleeps. After the user unlocks the device, all the activities resume and the fingerprint listener starts in the background. During this process, there's no stack change, so the foreground checking is not triggered this time. Another bypass is called multi-window bypass. Since Android 7, users can split the screen into two separate windows, but still, only one activity can be in the resume state at any given time, according to Android's activity management model. The window which the user is interacting with is active. The other one is considered inactive, and all activities inside will be stopped. So suppose the device is running in this multi-window mode. The malicious app in one window can do the confusion setup in its adjacent window. Then it can just wait for the user to interact with that window. For example, when the user resizes the window, it will be activated, and those activities inside will be resumed. Without any change in the stack, the mitigation is never triggered, despite the fact that there's a malicious covering. So system mitigations can fail and apps can have incorrect implementation. What about apps with correct implementation? Are they safe? Unfortunately, the answer is no. The last attack called risk attack can even make those apps with correct implementation vulnerable. The risk attack is enabled by a risk condition bug we discovered that can break the activity lifecycle model. If we launch two activities in a certain way, we can leave two activities in the resume state. In other words, the background activity is never paused or stopped. So no cancellation logic implemented by apps will be triggered in this case when a malicious covering presents. What makes it more powerful is that it can also invalidate the fingerprint mitigation we just mentioned. With all those attacks, one thing we want to measure is how common it is for apps to have improper implementation. To do that at a large scale, we design a static analyzer to check whether an app has proper implementation patterns. It constructs the call graph and checks for certain API calls for both fingerprint and camera APIs. The tool is available on GitHub. We scanned a set of over 8,000 apps that declared fingerprint or camera permission and found more than 40% of them contain some sort of implementation flaws that may lead to PHYjacking. We have sent several reports to Google and affected app vendors. The mitigation bypass we identified in the fingerprint API was patched in January 2021 with a CVE ID assigned. The patch for the risk condition bug is also ready and will be released soon. This diagram summarizes the Android system API mitigations for different physical input interfaces. Our study was mostly conducted when Android 11 was the latest. After Android 12 was released, we noticed a few interesting changes. For example, a privacy indicator was added to let users know whenever camera or microphone is in use. And tab jacking protection is enabled by default, system-wide in Android 12. With these new changes, attacks like PHYjacking is more difficult, but it doesn't mean that they are totally blocked. Actually, security researchers have proposed several protection mechanisms that could block most of these type of attacks. However, from what we observed, Android developers mitigate these attacks only by adding more and more simple checks. This is understandable since simple solutions are usually preferred in practice due to usability or maintenance costs. We think that in addition to current mitigations, Android can apply foreground checks to all sensitive physical inputs, not only to fingerprint. For some general purpose input like device like camera, the API should be designed to separate authorization and general usage, and more protections should be imposed for authorization use cases. So this is the end of our presentation. Questions are welcome, and for more resources like demo videos and codes are available on our website.